Hey, welcome to Coffee Compiler Club. Here today to talk about compilers and language runtimes and whether or not you can have incremental dominators or better aliasing or something going on. And we had the Discord channel discussion already running. And everyone's being recorded, and you show up on YouTube in a few hours. And with that, I was going to grab Haley, who is both not very commonly on Coffee Club, but also had a question about either aliasing or incremental dominators. And I twisted his arm to come and ask his question here.
Yes, this is all indeed the case.
You gonna ask?
Yeah, sure. Those are kind of motivating examples. I don't know, but I was just thinking that in my compiler, I have all the optimizations kind of run in a big loop. I do a whole bunch of peepholes, and we keep doing peepholes, and we do some more peepholes, and then eventually we run out of peepholes. And then when we're out of peepholes, we have some kind of things that would jam the peepholes that we want to try to undo in things. And if those manage to do any work, then we do the loop again. If we don't, then we're done. It kind of runs all this to a fixed point. I'll pull up the code because it's been a little while since I looked at it.
I was just throwing
See,
up your motivating example into the doc.
yeah. Which function was it? I think it was just called compiler. Compiler.
You wanna share your screen, or you wanna throw it up in the docs?
That's not really that exciting. Honestly, I'm just trying to remember what exactly it was doing. But yeah, it's just the one big loop, you know. So it does all the peepholes, then without peepholes, there's some stuff about inlining tail calls which we try to undo because those pessimize things, which is fun. And there's other big and slow optimizations that I only do sometimes.
Okay.
And yeah, I guess the problem is, when do I run? When's a good time to run all these slow optimizations?
So C2 runs the big slow ones. The only really big slow one he has is the loop ops. He runs the peeps to an iterate to a fixed point, just like you
Hmm.
do. I run the
Yeah,
big loop ops. They shred the CFT and they screw things around. Then I run the peeps again. The incremental dominators are fast and furious, so I don't count them as big. I run them once before the loops because I need it perfect, and I run them once after the loops get rid of reducible, and then the incremental one keeps it perfectly correct afterwards, sort of for extremely low cost. After that, none of the big things. There are no more big things in C2 until it's cogen time. So inlining happens way too early in C2. If I were
yeah,
to do C2 again, inlining would happen as just another peep.
yeah. That's what I do. Yes.
Yep.
Yeah. Here's the
So
link.
you have other things you're doing that need large restructuring, like tail call elimination,
Yeah.
which basically makes a loop
Um,
out of a tail
yeah.
call.
Yeah. Actually, well, yeah, sort of. Yes. It's the inlining has a case where if it sees a tail call and it walks up the dominators and it finds a matching start of a method it inlined, it will quote inline end quote by just making a loop back.
Just making a loop. Yeah.
Um,
Yeah.
but yeah, I think we discussed this earlier as well. That with
So
this,
so if that's done as a peep and you are reducible in the first place,
yeah,
you can keep the reducible, you can keep the perfect incremental dominators for low cost.
yeah,
But if you're inlining that to do that, you need to have a dominator algorithm
yeah,
have a notion of who is deeper in the tree be something you can insert in between.
yeah,
And the
yeah,
standard plus one with integers, you can't insert in between. If you had floats or doubles, you can
yeah,
insert in between like 50 times and then you run out of bits in the float.
yeah. That's one option. But the interesting thing about that isn't the peepholes and the inlines and doing the back arcs is quite okay. The issue I find is that at some point when we have, you know, because we keep around I call it scaffolding these nodes which indicate the start of a method and also the arguments of the method. So, when we do when we have uh, when we've made this thing and we have we're not really allowed to see through the scaffolding because the argument say the so we basically have phi nodes for all the arguments, but we haven't got all the phi inputs just yet, so we're basically not allowed to
Uh,
see through the phi at that point.
yes.
And because of that, at some point, I found that at some point I actually wanted to unjam the compiler. I need to start ripping out the scaffolding. And
Yeah.
it's kind of a balancing act when to do that, what to unscaffold as well. So that
Right.
also factors in.
So in the land of AA, where I'm compiling whole functions all simultaneously, every function who doesn't know yet who's going to call him has arguments which are basically, yeah, fees. I call them parameters, they have a little extra info on them, but they
Mhm.
have an unknown extra input that he doesn't know yet, and that's all the future to be discovered call graph bits. Um, for AA, I do a thing where the peeps don't go so far until I run the big optimistic algorithm for doing type finding as well as everything else. It's the standard optimistic algorithm, but it's both doing type finding and it's building a call graph as well as discovering the CFG. And as part of the call graph, have every function node. He starts uncalled, and then he starts picking up people as as the lattice falls, and he can't do any peeps because it's a optimistic pass. When he's done, he's got a full call graph. It's approximate, but it's a good one. And now I unbox you, I flip a switch and say, all you things are just fees,
Yeah,
and it's a done deal.
yeah,
And then at that point, yeah, at that point, it's just peepholes, including the things that do inlining or the things that do, I mean, whatever other things you're going to do, you can hold constants at arguments and partial inline and all kinds of stuff, sort of the normal things.
yeah, yeah. I think, dear.
But I'm stuck at functions unless I inline them until I get a call graph, which requires me to have an optimistic pass. So again, that's as far as I go because you're doing the calls as part of the whole thing. C2 inlines way eagerly, and the same story for you. If you want to make progress before you start doing other things, inline.
Yeah, yeah. Because I don't have any concrete examples because I fixed this a little while ago. It was like there was interesting interactions about what I need to rip out to allow what to inline, to what to tail call those weird interactions. And
Yeah,
I did end up with a heuristic which appears to work pretty okay.
there you
Which
go.
was, yeah, for um first off, I would rip out anything which didn't look like it could possibly get tail called back to if the method and the argument types don't match up, then they go away. And then if that doesn't work, then we just get rid of everything and hope for the best. When that seems to work fine
When you
enough,
say
I
get rid of,
guess.
you mean inline?
Um, good question. Um, um, oh dear. Let me check the code. It's in the inline, C of nodes inline file. I'm trying to remember. We have delete unused scaffolding. So that's delete unused scaffolding is
Yeah, I
the
don't.
things that don't match, and then force new inline specializations is when it does inline. So it tries to inline to generate new specializations because it also specializes at that point.
Right.
And then if that doesn't work, then we start ripping everything out. Okay. So it's those three cases in that order. Seems to work kind of okay.
Yeah, I don't carry like a ton of scaffolding. It's all just nodes in the graph.
Yeah.
So there's no rip out. I just let the optimizer do the normal thing to rip out scaffolding. But I don't inline everybody. And if you have a call to some other code, it doesn't necessarily inline. So the call is the scaffolding. It's a call node. It has its argument
Yeah.
inputs. It has a output results, which tie directly into the function header. So there is scaffolding in the graph, but it's just nodes in the graph. And when I hit the, singleton calls a singleton function, that one folds up. But other things require you to actually run a heuristic to say it's inline time and clone the
So
cache.
how inlining looks like in CF nodes? So do you copy all of the nodes? Do you leave some breadcrumbs to mark it that it was inlined? So
No, the breadcrumb thing is for perfect debugging like C2 does with Hotspot.
mm,
So that's a separate story. There's inlining and then there's how do I debug? And the inlining one is literally I take the body and I make a clone. A few other things I'll do if I have aliasing new allocations that have an aliasing knowledge in there, I'll clone them and change their alias numbers so you get the new here and the new in the clone are
mm.
independent aliasing, and that will let me maintain precision after inlining. Um,
What prevents you to, would it really help to leave some node that would mark it just to signify that this is the beginning of inline middle?
no, because you're going to optimize, and when you optimize, there is no well-defined beginning or end. That's the whole
Mhm.
point of the inlining.
Mm,
Like suppose I'm inlining a simple accessor. It's just
mhm.
a load. After
Yes.
inlining, it starts as a load, and then you run the optimizer, which says, hey, look for CSEs. Okay, the CSE first thing says, well, there's another one of these inline getters. It's also a load. I'll fold them up.
Yeah.
Suddenly, your 17 getters all became one load amongst
Mm,
all 17, and that's and then you want the load to float up and out and disappear, whatever, out of the loop and happen somewhere else. And there's no line in the sand that says I'm inlining or not. And
mhm.
you don't want that for optimization purposes.
Yes.
Yeah.
Now, the perfect debugging thing, which includes, hey, I've inlined or not,
Mhm.
is done by having places where you can stop. So save points, places where you stop. Just have a list of all the things that are in the machine architected stack at that point. In case of Java, it's your inlines and your arguments and local variables, and they're all inputs to the call. And
Yeah.
they're usually long-lived, not changing because you're inline deep, and so they all spill off, and the register allocator hides them away.
I remember that we talked that save points has are representable in source code. What a save point represents in source code?
Yeah, yeah, it represents a point in the program
Well,
execution. So whatever
entering a
necessary
function,
inlines.
what can count as a save point? So what?
Oh, well, C2 just throws them in such that you guarantee get them on all paths with about a frequency of one every 1,000 ops or so.
Does it for some kind of ordering maybe or some kind of structure in order to so
You get some forced okay, people are typing in the chat and
because
trying to
you can
use
still move things along, but I imagine that the save point should become some loosely
Max, is that
ordered.
resource? It's recurse.
Recurse.
Okay, fine. You've been cursed again.
Hmm.
Yeah. And so my high school yearbook quote was recurse is called again.
Yes. Okay, fine. I'm sorry, Theodore. You're
Yeah.
asking what is the limits or structure of how these things happen?
The save point I remember that we talk about that, and you say that save points are exactly representable in source code. What would that mean? Enter of a function or something. What would generate a save point?
Yeah, what the points that generate a safe point? Well, okay. So you start by putting one at the parser puts one at every point where he can't tell that you might not have a loop. So it's every function call, which might be self-recursive, and
Okay.
every back edge. That's
Yeah.
too many, especially after some inlining or loop unrolling or whatever.
You said the parser insert them artificially, and so
Yeah,
it enrich the IR. Okay.
yeah, enrich it. Yes, yes.
Okay.
He comes to a point like a function header, and he throws one in and says, "Here's the current state of the world." It was a safe point in the interpreter. Every function call is already.
Mhm.
So he just throws that in, and then he carries on with the IR, and then the safe points are all read onlys. So they don't update anything, but they read everything. So they do mess with your optimizations, and then he looks and gets rid of extras. So after he's done optimizing for a while, he'll have paths which have safe points that are 100% post-dominating another safe point. He picks one, tosses the extras.
So it sounds like there's no rigorous math to where you want your save points. It's basically a pile of heuristics and
Yeah,
more art than science.
yeah, it's a pile of heuristics. And there's not much science to it. The trick is that you just need to allow GC often enough. And if somebody wants to do a breakpoint debug, you want to not have them run too far. Like if you're thinking about your program and it's running as fast as the CPU runs, and you hit the I want a breakpoint, stop me now, then how long between you thought and the program actually ran? And that the answer, of course, is a couple milliseconds most. You're 10 milliseconds for your click time or whatever. So it ran a few 100 million instructions. Who cares every thousand which one of the safe points, one of the bazillions of safe points you ran over you took? You pick one at random. Bank. Okay, that's the one you got. And that's where, and you get a perfect answer at that point, and you've stopped. Now, if you set a breakpoint in code and you want to stop exactly at that breakpoint, then the system intercepts the safe point in the generated code and marks it as you must halt here now. And there's a couple ways to do that, depending on your cost model.
I assume you also have to have them before certain kinds of side effects.
The safe points read everything and write nothing. And so they read all side effect things. So that's an explicit edge in CF nodes. All side effects are an explicit edge in the CF nodes. That will force a serialization such that the safe point will happen the correct order relative to your side effect.
But I certainly don't want
So
to like send an email and then hit my debug point and then go back to the previous save point and then send the email again while getting back to your debug.
No. So you say go backwards. So Java has no go back in time. This is not a reversible debugger. No Java does this. You can pop frame and rerun, but side effects that happened in the frames that you ran to hit the safe point, they happened. When you pop a frame and rerun and get back to that same breakpoint, you rerun those same side effects.
you said that the save points enforce some restriction on the peepholes that can be made. What kind of restriction?
I'm sorry, restriction on what?
Your restriction on the optimizations that can happen between the
Yeah,
save points or something.
yeah, they keep things alive.
Mhm.
So the obvious thing is I'm running a loop and the loop's doing a DAXB, and I've done strength reduction because I'm a good optimizer, and I'm loading from a pointer plus plus and multiplying by pointer plus plus and storing, and I don't need the index variable at all. I have the array base, I have a pointer in the middle, and I'm walking my pointers through the arrays and I'm doing my math. I don't need the index variable.
Can I
Well,
ask
the
you,
safe point says if you took a breakpoint in the middle of this long running loop, you'll get the index variable. So I have to have some way to manufacture an index variable.
can you type this out in the doc and just for visibility?
Can you share?
Yeah. Okay. So somebody says at the source code level for and I colon in A sub I equals B sub I times C sub I, and it's big math and it runs a long time. So this is assumed bit. So then there's a bunch of optimizations that might happen, but a thing that could happen here is something that looks like star, let's see, star pointer to A plus plus is equal to, star pointer to B plus plus times star pointer to C plus plus, and also until pointer A is equal to, unequal to, or less than, pointer N. So that might be an optimized version, for instance. And yeah, it's probably been unrolled, and so other things going to happen on here. But so you can imagine this. Okay, there's no induction variable here. I stop in the middle. Stop in the middle. What is that? Right? Okay, so what might happen, there are a couple ways this could be solved, is that the optimizer, the safe point in the loop, demands a value for I. So there's actually a save point here. He reads I as an input. So if I stop there, I can hand you the value for I at the debugger. And that means he has to do the math on I. So there is, some value for I, and now an optimization that didn't happen is I lives on, and there's a plus plus. So you didn't get rid of I out of the loop. Now this particular example, I can get rid of I out of the loop still, because the actual save point is something like if very rare, so some very cheap, very rare test, then save point. And then the fix here is to say, I is a pointer in minus pointer A shifted right, or something like that. However, or whatever, shifted right by 3 or 4. So some math like that gives you the value for I at a safe point for the cost of a very rare test.
So to me, a save point sounds like you can stop and look at the nodes and look at the variables.
Yeah,
so
it'll have A, B, C as array bases and whatever other variables your program has here. Yes. Is as if it's a function call that is rarely taken and reads all the variables, including all your inline state.
So it's solely for reporting purposes or something else?
So there are two normal things that happen periodically in a garbage in Java as a runtime, but the garbage collection for garbage collected languages that are multi-threaded need to have a way to stop a long-running thread like the stack be doing no allocation, so he can stop the world and do garbage collection on behalf of another thread which needs to allocate. So there are GC points. Hotspot mixes GC points and save points. And then, Max points out sampling profilers. Absolutely. It turns out that the standard sampling profiler you get from like your kit and the like, they halt at save points, take a sample, and they run. I call those save point profilers because there are places where C2 won't insert save points, and you'll never get a sample there. There are hot loops which C2 can prove in a reasonable period of time, and he will not put a save point in there, and the loop is hot, and you will never get a save point profile. Okay. Random stack samplers don't suffer from that, and they'll get you a stack sample, but they require some more care that your random stack is actually parsable. And I did that at work at Azul, but not for Hotspot. Like a Hotspot, as I left it, couldn't do random stack samples. He would crash periodically, or he'd have to give up on some samples. And he had a very low, rare, frequently case where he would fail.
In current JVMs, the async profiler gives you that, or at least it doesn't have the safe point bias.
Okay. Yeah, I knew that there was a way to get them now. Azul, I did that work, like I said, some time ago, and it took a while for the OpenJDK to catch up. It's out there. Fine. Yeah, so safe points like here read all the state. Now, A, B, and C in the example down here aren't being used in the loop, and if I ran out of registers, I would spill them, and the safe point would take them on the stack, and that would just go into the debug info. So they don't consume any registers. The safe point doesn't consume registers for things that aren't being used. So ABC had to be computed somewhere that got passed in where they came from. They got spilled to the stack. But he may require you to keep things alive that would otherwise be dead from the compiler's point of view. So it's not zero cost, but in practice, it's so low that no one has been reliably able to measure it on any reasonably large program. So there's some micro benchmarks you might be able to measure save point costs, but any large program, it's well under, it's a 10th percent below the measurement bias. And you can stop any point and get a valid debuggable program at that point.
So a save point is witness of the program state.
It's a witness of the program state, yeah.
Okay.
Now, to speed up this version here, what really happens is unroll and jam with the save point removed. So this thing here becomes like, so that's 4 at a time, but the pluses all happen at the end. I don't want to write all the math out. And the unroll and jam says I put another loop here. For here, it's 64 iters. Oops. And then there's if at least 64 iters do this next set here. And then you get a safe point outside of it. So now the inner loop gets unrolled enough times that it touches cache lines at a shot and can now be SIMD-ized. Like I say, at least 64 iters up front, they'll also be, hey, and do the odd layout cache line misaligned bits first. Now I can hand you an inner loop, which is enrolled as much as you want, cache line to line in all directions, and has no safe points. And then there's SIMD ops in there. Okay, every now and then, every 64 iters or so, you stop and do a safe point check. Well, that's less than 1,000 clocks. So again, you can't measure the overhead of the safe point or see it, but there's no performance cost.
So for a little loss of precision, the save points become cheaper because
Yeah, that's what happens here. And C2 does this. This is unroll and jam. C2 is doing unroll and jam.
Okay, cool.
And the alignment and the SIMD and all that kind of shit that's going on. So yeah, I don't know what else we're doing inlining. C2, the parser walks the inline stack when he builds the safe points, and they have chunks of arguments for every inline depth they're at so that you can do that. The other piece of course, is that the safe points, because they read memory state, prevent writes from bypassing.
So the inline threshold is configurable in the JVM, I believe. But
Yeah.
I remember way back to discover what methods to inline. I remember you said something that you get the profile data and where is a steep slowdown. That is the amount of methods you inline or something. Because
You're looking for places where there's a loop with a large drop or something. So there's like you have a stack trace. You have function 0 is cold, so low entries, and function 1 is cold and low, that means low entry counts, and function 2 here is medium, and function 3, so the stack's growing down. So this is a stack trace I got.
Mhm.
And I stopped at function 4. And this is where I took the 10K trip, right?
Mhm.
Well, okay, so I crawl the stack up and I say, well, 3 probably calls 4 because it's relatively hot. So let's call this one, 9.5K. It has some cutout, but it was typically calling function 4. And the
Mhm.
medium guy was at 2K. And this guy was at 1 or 10 or something. And here's his main 1. This is main.
Yes.
So somewhere in here, I stop and I say, geez, I probably should inline function 4 into 3, 3 into 2. But here's, I have a ratio between cold and medium here. The ratio here from function 2 over function 1 is whatever, it's 200, something like that. And I'm like, oh, that's a good point to stop. So I'll go make function 1 a loop header, a function entry point. Now inline, 2, 3, 4 into it. And almost always function 1 has a 100 plus running loop who calls function 2 who has 100 running plus loop who calls function 3 who calls 4 directly. And there's a few cutouts there, but generally you get the hot loop nest right there.
So this is like the flag when the inlining
when it's time to
starts, and from there you discover how big of a chunk you want to inline.
So
this is the most beneficial, and it's determined by the ratio.
I started function 1 based on the ratios of what you're going up. There are a few other heuristics thrown in because you often get a lot of piddling warm things. And if you inline everybody too much, you get iCache blowout. So there are some rules about where it's wishy-washy, but you get these sharp cutoffs. That's always you take that always. Then from function 1, while I inline 2, 3, 4, I also look at who function 1 calls otherwise. and make decisions on them as well. Because function one may be calling some other things that are medium hot to get hot or whatever. I said I found function two calling 3 and 4, but function two calls us 5, he calls 6, calls 7, also equally hot. So they all get inline together. So it's not that you just inline function 2, 3, 4. You look at each inline point and you inline more based on the profiles you find.
So this has become entirely different at each point when you inline code. So the code becomes very different when you start to make
Yeah,
code.
it's all based on these counters, and the counters are somewhat statistical. If it's all done on purely single-threaded with very deterministic things, you can get very reliable inline patterns. If you have any sort of timing going on with multiple threads and background people doing prints and shit, you'll get different counts, and the inlining heuristic will give you different numbers. And that led to this long, involved history of how to benchmark JIT systems. And the answer came back is that you have this compile plan, and at any given run, you might get one of several compile plans that were popular plans for this point. The important plan for the performance might give you one of 3 options. And one of the options gave you a pretty good answer, and one of the options gave you an okay, one of them gave you a suck answer. And you had this trimodal distribution of your performance based on the inlining pattern. Now, if you just took the same JVM and kept running it more and more, the inline pattern never changed. So you kept the compile plan, and there's a good paper out there about how to deal with compile plans in JITs. So you have to restart the JIT from scratch. It is not correct to say, in the same JIT, I call it, and then I call this other thing, and I call this other thing, and it came around and called this guy again. You got one compile plan, no matter how many times you called things, and maybe it was the good plan, and maybe it wasn't. So you have to restart the JIT to get a new compile plan. And then it's pseudo random off of some amount of there are some easily targeted compile plans you're likely to get. So you need to run a bunch to see that you always get the same compile plan, or you get a couple different ones. And if you get a couple different ones, you have to figure out which ones you're getting and how often, and that turns into having a standard distribution.
Restarting the JIT roughly means wipe the state of the JIT and allow it to run again.
You can't. There's no built-in thing that says wipe all your JITted code out and rego. We could argue that there ought to be a compile beam for that, although that sounds like an easy way to commit suicide by accident here. Let's see. Profiling Java with compile plans. Let's see if we get a scholarly. No, we get. I'm not. Let me try Google Scholar here. There's some floating around. There are some canonical papers about. No, these are all about the current stack profiling involving accurate random stack sample versus safepoint. All right, so there's papers out there about this that people figured out after a while that they were getting bad answers.
There are weird things you could imagine a profiler doing, though. Like, I look at my function, and even though it's straight line code, 90% of the lines in my function are run 1,000,000 times, and 3 of the lines are only run 1,000 times because it knows that they got lifted out of the loop that called the function.
You talking about here's Heinz. What the heck? I'm
You run
sorry.
into like a similar problem with with normal sampling profilers, because out of order processors effectively do the same thing as like safe points.
Yeah.
So it might be like, this compare is like really slow. Why is this compare stalling? It's like, well, it's not the compare that's stalling. It's waiting on the load that the compare wanted.
Right.
And so the compare isn't slow. It's waiting on the load that's slow.
Yeah.
And so the actual slow bit is even potentially like 50 instructions away.
Another thing that comes out of wide issue is that certain ops will always wide issue together, and you'll never take a random stack sample break in between the wide issue set.
Yeah, that one
But-
comes up a lot with like compare and jumps because those get like macro opt.
Yep. Yep. So you'll never get the breakpoint in between the two.
Mhm.
Same as the SafePoint profilers.
In the JAX RVM, I think this arrangement is called the pseudo-adaptive, but I'm trying to find where that originates. If there's anything on that, I just know in all the GC papers which use JAX RVM, they say we use the pseudo-adaptive, which does just that with the configuration. Speaking of, I put the paper, what was it called? The one safe point overhead, yield point, stop and go, some such. They say for Jake's RVM, the average safe point overhead's like 2%. The maximum was 10%.
Okay. And that was SafePoint overhead counting all things related keeping shit alive and stuff like that. Yeah.
Yeah.
Okay. I looked on and off at C2, both at Sun and at Azul, and it was I never had it as high as 10% unless it was kind of an artificial test case. Somebody was trying hard to force something ugly. And they often used compile flags. JVM flags that dicked with the compiler to get there. The flip side was that I would not put in safe points where Azul wanted them because Azul wanted to run the background GC more often. And they wanted the safe points to cut down latency for like those high frequency trader guys who actually were fond of running long running big loops doing giant math for whatever moment and also wanting low latency when they were deciding to.
Right, but if you want microsecond pause times, does that force you to have your save points closer together?
Yeah, right. So their threads that were doing the fast response weren't running these giant ass loops. The giant ass loops were running because they were trying to keep up with some market math thing that were running in the same process space so they'd have access to it. But that meant the long running loops might dick around with the safe point. And eventually Azul beat safe point profile. We treated we treated stalls for anything in the JVM as an engineering bug. If they exceeded a certain level, it was considered a bug. You recorded it, you did engineering things to it. As soon as you put it in your engineering process, you could start getting a handle on where the delays are coming from. And there were some, and that was when Roll and Jam came in, and that turned off all the C2 ones. And Gil 10A fought a long time to not get rid of fixed length loops, safe points, but they were never the tall pole in the tent after Unroll and Jam came in. The tall pole in the tent was always OS related things. Why did you stall? Well, we were furiously zeroing pages and the kernel decided it had to zero a page and it was not going to take an interrupt or honor anything until it finished zeroing some count of pages. And that was the stall. The guy ate an interrupt and it didn't respond because the kernel said, Mr. Interrupt, wait, I'm going to zero this gigabytes worth of memory. Now I'll take you. So that had to get fixed. There were several variations that all turned into the kernel wasn't happy. For a brief while, Gil was like, hey, we can do VMs for this. And I was like, you got to be freaking nuts. And sure enough, the VM was so terrible at random safe point crap. So that went back to bare metal Linux kernels with carefully tweaked kernel flags to shove the interrupts off to the side and get the page zeroing thing fixed and backgrounded and made a little more less bulky, a little more incremental. And there were, I don't know, 10 or 20 other things. Azul did a bunch of things in the Linux kernel to make it more responsive. And then they got to a point where they could get these low microsecond pauses, but it got away from the JIT pretty soon and got away from the GC pretty soon, and it turned into kernel things.
It does kind of amaze me the cost that VMs have even today.
I'm all about, like, you got to be kidding me. What are you using a VM for? Why is it really save you that much? Okay, maybe something's going on there. It's saving something to somebody, but yes, there's some real costs there.
I'm a little surprised. I was like wondering if it would be fast if the kernel only did 4K pages, or a single 4K page at a time. so all the data is in cache, but I don't know if it gives you the L1
It
cache.
depends on what you're asking for. The Azul collector would grab gigabytes and gigabytes at a time, and then free gigabytes and gigabytes at a time. And then the expectation was the kernel was going to 0 gigabytes and gigabytes at a time.
Yeah, but isn't all that memory unmapped until you touch it?
That's the point. The GC is mapping and unmapping at a tremendous rate. Gigabytes a second, it's probably closer to terabytes a second. It's a ludicrous rate to run the low pause GC. It's mapping and
Would
unmapping.
it speed up that if you tell the kernel to prefold the pages in larger chunks?
I didn't mess at that point with that stuff at that time. So I know there was a bunch of work done, and I don't know what it was. And it was around page zeroing latency was one of them, but there were other things they did too. And again, as Lee was saying, hey, make it smaller counts. I think they did fewer at a shot as opposed to smaller pages at a shot. We didn't, the GC didn't ask for 4K pages. Threads asked for 4K pages. The compiler, the running system doing code gen actually really didn't want 4K pages either. The 4K pages were for page guard on threads. So everyone else was always getting whatever the big pages are. It's 2 megs or something, whatever big pages were.
I haven't measured it too much, but I do know that when I remove the reserving memory that pre-faults it, when I removed it, it went a lot faster, like a couple hundred milliseconds faster. But the compiler was only running for a second, so.
So the issue with doing that for something like a low latency GC is who's doing the pre-faulting? Because if you have the GC threads doing the pre-faulting, then you've slowed down the speed of the GC thread. And if you have the mutator threads, just spam it out all at once, and you've created this big hitch.
Right.
Because each one of those is going to be it's in the realm of microseconds to do one of these initial faults, just because seg faults are slow.
Yeah. You want the GC to go do all that because it's got no rush.
Yeah.
I've got one benchmark, one of the particularly nasty ones, one particularly nasty micro benchmark, which spends half the time, because it spends half the time in Linux kernel because the GC is very frantically mapping unmapping memory.
Yeah. Okay. And this is your GC too, though, right?
Yes.
Okay.
Yes. Yeah, and also the original one and Steelbank Common Lisp is also like this because it's quite eager. Well, it's somewhat eager to give back memory to the operating system. In this very specific benchmark, it is much too eager because basically what happens is basically this it's Steelbank has way too many generations. It's got 6 of them. Most people have 2. I don't know why there's 6. No one I know knows why it has 6. But anyway, what happens is it will unmap memory when it's collecting anything older than the youngest of generations. But this benchmark isn't particularly generational. So it kind of just keeps doing these medium-sized collections which keep mapping unmapping. And I'm not really sure if there's any good way to spot, hey, this program isn't very generational, maybe we should put off unmapping, remapping even later than this.
I'm sure there's a heuristic you can gather somewhere, but is it worth it?
Yeah, it's just one silly program. On the other hand, one silly program, which I will admit did make my benchmarks look a bit good, because this silly program is also really bad for copying collectors.
Oh, I see.
It's pretty good for non-moving, so this happens to be somewhat convenient for me in some regards.
You know what? You do what it takes to get your PhD, and you get out. If the advisor thinks the numbers look good, he's going to sign off because of that. Well, you're done.
That drove me crazy when I first started and was like, can I please have all the requirements for the PhD? And my advisor was like, your requirements for a PhD is to convince me and 3 other committee members that you have a PhD.
Yep.
And I was like, that is not actionable advice.
Yeah. I that too.
Unfortunately.
did this cool fast compiler thing, and they're like, no, fast compiler's not worth a PhD. So I did this fucking piece of math. Then I got a PhD on a piece of math, and I have a giant appendix on a fast compiler.
I just left.
Uh, no, I got my degree. It was worth it to get the degree. In the long run, it's worth it.
No.
I guess in retrospect, your like PhD thesis is technically about the like combined like constant propagation stuff with the global value numbering, with the identity stuff. But like that's like, while that's like cool, the cooler thing is like, oh, let's do SSA without a global schedule. Let's do, combine the other optimizations. Like
I said, I did what I did. I got my degree. Yeah. I got out, and that was, we're not going to give it to you for having a fast compiler. Nope. So I added some math.
Yes. Alas, the GC, alas, is not university work. Alas, people ask me, is this for university work? No, just
you have to get the PhD done.
Yeah.
It's worth it.
Yeah.
And the longer you stall, the harder it gets.
Yeah, alas.
And GC is a pit. It is there is no bottom to the end of GC.
Yep. Yeah. That's fun. It's not university work.
Is it paid work?
Is it paid work? Well, for some time I was taking donations.
That doesn't count.
That doesn't count.
No,
oh well. Okay. Oh well.
It
Shame.
counts if you're getting enough donations to be the equivalent of a full-time salary of an engineer.
If you're running for president, you probably get donations that are sufficient.
Yeah. Yeah. Unless I'm probably
if you're
apparently the people that do NTP get like $60,000 a year for the three of them.
Something like I'd be something like a one to two orders of magnitude off of that. So
yeah. I say, what's your hourly rate under your current donation level?
No, don't ask.
That I claim, put it aside and go get your PhD.
Yeah,
it's fun. Put it aside, get the PhD.
It's a love-hate relationship with this GC. It's fun sometimes.
Okay, fine. Get your relaxation however you get it. I mean, I do my things to get relaxation.
Well, hey, sometimes it's not relaxing. Sometimes it's the opposite of relaxing. And in those cases, I don't work on it.
All right.
Not everything is about salary. When I was a grad student, the undergrad researchers in the lab decided that they would make a timesheet for me and track all the hours that any of them saw me in lab, and then showed up to me with their spreadsheet explaining that I could make much more money if I spent the same number of hours working at the Burger King than working in the graduate lab. And I was like, that's so sweet. The undergrads are looking out for me.
Yep.
Trying to.
Yep. That math went around Texas A&M a lot as well. Should I be a plumber or should I get this comp sci degree? And the answer was, well, a plumber would make, 70, 80K 40 years ago in Texas. Right then, that was pretty good money.
The moment that hit me hardest was when I was doing one audit and I managed to see one of the bills that my time was being charged out for. And I had been paid $12.50 an hour for work that was being charged at $3.50 an hour.
Wait, you got paid?
I got $12.50. They charged $350.
$350. Yes. Oh, more than 10x. Wow, like 5x I've seen fairly commonly, especially out of universities. That's somewhere between 2 to 5x, but not 10x or almost.
But yeah, when I went from grad student to Google engineer, that was in percentage terms a pretty good raise.
Oh yeah.
Well, I'm still undecided on if I should go do a PhD next year or not, or any year rather. Doesn't have to be next year, but should I? I'm undecided.
All right, pitch us on what you want the research to be.
Oh. Yes, but I suppose that would be a good start.
You want to do something that you like to do, but you want to get paid for it as well. like paid real money for it.
Also, you don't have to have the research topic, but if you know there's interesting people who you like working with, that's
Yeah,
also pretty
yeah,
compelling motivation.
sure.
Yeah, fair
That's
enough.
true.
Yeah, actually, right. Working with dicks is a painful thing. Yes.
Yeah.
And I guess I've been
Well,
there a number of times.
well, I don't know. I think I might have accumulated some opinions on how to make non-nasty runtime systems. Since no offense to anyone involved, I have worked for a little while on a particularly nasty runtime system.
You're not talking about common list or steel, whatever common list.
Steel Bank?
Well, I'm not talking about it.
Okay, you are. Just not a common list guy. Not a problem.
No, no,
Uh,
no. It's the runtime. The runtimes. The runtime has particular assumptions they have to break everywhere
yes.
because for all of its existence, it's had a basically fully copying generational GC, and here I am poking holes in that, and it does not like that.
Hotspot went through a number of rough transitions while it picked up several different GCs and several different compiler ways of handling the stack when you threw exceptions. That was the grief part. We did sort out relatively quickly how to install code and code dependencies kind of quickly. Like what C2 declares as a dependency and what C1 declares as a dependency are very different. There was a lot of,
Dependency meaning?
oh, C2 says you have no inlines.
Mhm.
You have no inlines. You have no subclasses. So I'm going to just take the inline and be done. You have a class X, it has no subclasses. You make a virtual call, it can only be to an instance of X. So I'll just inline X. Now I need to go tell the runtime, hey, if a subclass of X shows up, okay, that one has been in for a while. But then C2 would say, hey, there are exactly two cases here. You have an abstract byte buffer. He has got a heap and a direct. There's exactly two. So I'll do an if test, and then it's one or the other. But if a third one shows up, I need to blow out and re-go. So when somebody wants to say load a third direct heap byte buffer subclass flavor, the class loader has to stop and say, wait, you can't load this until I first blow away everybody who's used C2 to go compile byte buffers.
So the decisions are made as if ahead of time to compile. So I've only seen these two instances of the classes, and I pretend that there will be no more.
Right.
If there will be no more, I will suck it.
So I mean, C2 comes along and says, hey, this field's a zero as a global static. I'm just going to pretend it's always a zero. Please, Mr. Interpreter, if you're going to write to this field, this global static, stop, don't write, first talk to me. Intercept the interpreter where he's writing to a global static. Intercept the runtime when he's loading this or that. Hey, I want to do, I don't, they're like, turned out to be like 50 unrelated things that C2 ended up with, and C1 had like 2, 3 or something. It was huge count of different things going on there.
So it's highly speculative, but it is the nicest thing in the world when all of your assumptions turn out to be wrong to bail out the interpreter and start again.
And then you get all these race conditions where people wanted badly to load and couldn't or didn't check the right order or you didn't blow the code away. So the worst case scenarios here were I said I'm done with this code. There is a function that's currently running who's in the middle of running and has nested into some deeper function underneath. So stack trace going down, this guy is going to get blown away. I'm running down here, but I need to unwind into this stack trace. And how do I do that? And then this guy unwinds rapidly, and I'm in the middle of trying to dork this stack frame so that I can make it suitable for unwinding, and there's a race going on. Who wins that race, and what order does it happen in? And many early versions of things blew that, and you'd have these weird crashes that only happened rarely when somebody touched something and some new code showed and some old code had to blow away and some background thread turned out was middle of running, was trying to unwind the stack and you were busy hacking the stack to say, don't run this code anymore. And it's too late. You already ran it and whatever. Those were a lot of
we talked
nasty things.
about I believe, but does it throw all the data, all the abstentions that were made, or someone kept in for a reuse, for example, in situ, for example?
You're talking about saving the generated code for a later run
Yeah,
of the JVM?
saving some kind of the skeleton of the decisions were made, so you can. So
That's
there are some good
right.
decisions made. There are some bad decisions
Or
made,
at
but
least counters from previous runs.
Oh, okay. Yeah.
or
Right. So let's just break out. There's like two directions here.
yeah.
Arthur's doing in the Falcon work a complete, I'm saving everything and I'm running that profile data into LLVM and then I'm making that code. And then when I start up, I grab my pre-baked LLVM code. And he's been working on that for quite a few years and has gotten some reasonable successes out of it. So he's not here. I don't want to speak for him, but when he's here, it's a great question to go ask how far he's gotten, because I know he's gotten pretty far. In C2, there was always in the runtime, the profile data was kept around. And in particular, if you made a mistake, if C2 said, this is never zero, and so I'll just put the fast check in, which is I'll load through a pointer and it'll crash on you. It'll give me a hardware NPE if it actually is zero. So the test is there, but the check was done, very expensive if it happens. And then it happens. So I want to recompile saying, well, this guy might be a zero. So I want to put a bit somewhere. We call those heroic optimization bits, and methods had to accumulate them. And so methods and their inlines would have to accumulate them independently, because I have some big method hierarchy and I had this smaller method inline here and inline here, and they got separate profile data. And C2, the next time he inline, would have to inline this guy and this guy independently to get at those independent profile datas. And that was a big pile of work to get all that sorted out as well. And so the other one is that C1 would do the small inline, and you wanted the profile data from he inlined even smaller guys down here. So you wanted whatever C1 did, you wanted to inline at least that much. And then you had multiple instances of at least that much going around.
Oh, you said C1, yeah, C2 is repeating the work of C1.
Yeah, the three tiers. I mean, Azul did three tiers for a while, but OpenJDK had three tiers for quite a while. I think they used a cut down C2 instead of a C1, C2, but
so you don't grab the optimized code from the previous compiler. So you just how that.
So okay, so then the reason that Arthur's taking code from a previous compiler and going is because he wants startup time, and he has a slower jet because he's using LLVM as a jet, and it's way the hell slow. The difficulty with that is that your proper Java semantics are that, like, your class initializers run at the first touch. And a lot of your class initializers come from, like, network packets showed up and you took a network interrupt and you're doing a thread that came over the network, and his order of his initialization is different. So when you come to some C2 JITted code and he knows he wants to call something, at the time that he's first coming in on the second go round, he wants to grab the old code and bring it in. That class has not been loaded yet. Some inline subpiece has not been loaded yet. So he's got a big old wad of code, but he can't run half of it because the class in question doesn't have his initializers run yet. He can't run that code. So he can't take the whole wad, and he doesn't have any way to slice pieces out of it and say, this part I generated code for has to wait until the class gets initialized, because he's not, he makes that check before he bothers to inline. So at the time he generated the code, it had been running and was inline. We're good to go. The time he grabs it, it's not there. He doesn't want it inline. He can't. It's not legal to go run the generated code. So that's a hard problem to go sort on. And that was the reason I bailed out on that. And then I got busy with other things and never looked back. And it lived that way forever and a day. And, I think Arthur's trying to do it the right way. A bunch of folks tried, and the usual story was they just cheated on the semantics, which is why they never got sort of mainstream attraction.
But we discussed that C2 and C1 have a profile compatible data, so it doesn't convert anything. It just took the profile data in.
Yeah, the Azul stack had C1 and C2. The profile data was compatible. It was kept alongside methods typically. So if I have C1 methods, and I JITted this method here, and I put counters in, and he had some inlines within him, then he said, at this method and then at these points within it, I have inline methods, and then the inline methods had entry and back edge counts, standard things the interpreter would get you. He may have had some other accounts. He had a couple other accounts.
So even though the code that they generate is not compatible, the decisions are transferred.
Yeah, the profile data was compatible and on purpose. I mean, the C2 wants badly to read C1's counters.
Yes.
The cost to the interpreter to do profiling is like double the cost of interpreting alone. Like it's very expensive for the interpreter to profile. The cost for C1 to profile is, Shaw's saying small. It's small because you can generate all the offsets into where you're putting the bits at compile time constants, where the interpreter has to redo the math dynamically every time. So somewhere in C1 at the very start, it says, well, I'm doing method X. I'll know that if I go to method X and I grab this other field where the profile data is, I have a wad of bytes that I've preset up, and I know exactly how big it is. And at these offsets, I'm incrementing counters. So I have a base of profile data I'm generating, I just put it in a register. And whenever I need to do a profile, I do add plus plus, add offset, boom, profile count done. And Artur is now joining an hour late, but if you wanted to ask him, that here he's going to be here in a second. Artur. So we were just talking about how far you got with Falcon and reading profile data from prior runs for use in generating code for the next run.
Right off the bat.
Right off the bat.
Yeah. So that's what we call ready now. That is, initially it was just a mode in which you can dump the profile, dump the log of compilations with all the associated profiles and class hierarchy, states, etc. And then you can read this profile in a subsequent run, and we would do a couple of things. So first, we would proactively trigger compilations when the class hierarchy in the state where the compilation can be done, like necessary classes are loaded and initialized. And then when we trigger a compilation, we will use the profile from the previous run for this compilation.
And not a profile you're collecting on the current run.
There is actually some merging of live profile and remembered profile. And then one mode of operation is when you have a training run, you generate the profile. You have a canary environment where you run and collect the profile, and then you distribute this profile on all the instances you have. This is one mode. The other mode, what we call rolling profile, is when every time you restart, you save the profile and use profile from previous run. This way you can learn from rare events and deops that happened across multiple runs.
Right.
So that's another thing. We remember speculations that failed, and we would not do them if they failed.
Optimization bits.
Yeah.
Yeah.
So, and then this is kind of the standard way to do ready now. Somewhat recently, we also introduced a way to have it, instead of files, have a service that would manage the profiles. So you start your VM, you give it a name of the application, and then the VM talks to this service, and A, shares the profile it has, and then B, gets the profile. If the service already has the profile for this application, it will get it. So this way, in cluster environments where you may not be able to conveniently save and reuse files, we can still do this kind of profile sharing across different instances, across different runs.
Right. You're profiling the cluster as a whole, more or less.
Yeah. Yeah.
So when you're waiting for all the classes to load so that you can run your profile, which has all these inline classes that aren't there yet, are you able to compile things that are partially there and have their classes partially loaded?
So we have so-called soft wave and hard wave of compilations. So if we need the classes to be loaded, but then for some of the classes, we need them to be initialized. So let's say we can propagate static final fields, etc. So if all the conditions are satisfied, we can do the final version of the compilation. That's what we call hard wave. But if we only have loaded but not initialized class, we can still make a compilation, but A will need to have class initialization checks and the code that actually triggers initialization, and B will be limited in what kind of optimizations we can do. Let's say static final fields are not available.
Okay. So you actually use the prior profile, but you put in all these checks to say class is not loaded yet.
Yeah.
You try again after a while? Like once the class is all loaded, you go back to the hard compile?
Oh yeah, first we'll get the soft dependency satisfied. We'll just have to have the classes loaded. But then when the classes that need to be initialized are initialized, this will mean that compilation has hard dependency satisfied. And maybe we will just replace the compilation in the compile queue. It happens quite often because classes are often initialized right after they're loaded. Right. Or maybe we'll replace a live compilation that has been executing for a while.
Yeah, okay. But you will swap out a live compilation. That was trying. A live active code.
Yep.
Yeah. Okay. Cool.
So it is. I think at this point, most of our customers at pilots are using Ready Now.
Okay.
So it does involve some extra setup.
So
it has some operational complexity, but yeah, the benefits are great.
So it pays off. How speed up roughly we are talking reusing that?
What it does, it improves warm up because we don't need to wait for code to get hot and accumulate the counters. We proactively compile stuff. And B, we eliminate de-opt events, and we eliminate these.
You don't get the de-opt
high percentage. Yeah. So
because you already took the de-opt in a prior run and remembered that.
So historically, this was a feature that was requested by a lot of trading applications, because what an adaptive runtime does. So a typical trading application sits in a loop, checks for some conditions, but only every once in a while triggers the trade, triggers the transaction. And what adaptive runtime would do, it would optimize for just sitting in the loop and waiting for conditions to be right. And because we had C4, trading applications really liked us for low latency, but they had this issue that, adaptive runtime was adapting for the wrong thing. And that's how Ready Now appeared. But then it turned out that it's useful in all kinds of applications.
So just to be clear, when the rare event happened, that's when you wanted the low latency, and that's when you took the de-opt and recompile.
Yeah.
No, it sounds like a good answer.
Okay. Thank you, Artur. Thank you.
Yeah.
Artur, out of curiosity, are you saving LLVM IR after previous compilations, or do you start from Java bytecode, for example, each time?
So Ready Now itself doesn't save any compilations. It saves a profile and kind of compilation log. So we start from scratch.
Okay, so just compilation decisions, but not compilation artifacts or compilation IR, so to speak.
Right. We also we have a feature what we call compile stashing. It was our first attempt to implement caching of compilations, and for that we, as a key for this kind of compilation cache, we saved the initial IR and set of queries that we asked VM for during the compilation. So when we have a compilation, so basically we have a cache. It's keyed by initial IR and all the queries that the compiler asked the VM.
And then you just skip the cogen phase, basically.
Yeah, we know the input for the compilation. We know all the facts that we used. And we know the result it produced.
You changed your mind, so it wasn't working well. Why not?
So it works kind of moderately well. There were some problems. So first, without Ready Now, because of profile differences, there were just too many differences, small differences that the front end did something like.
Yeah, that's what I was thinking. You'd be hidden by. Okay.
That's one thing. But with Ready Now, because we in many cases have fixed profile that we like stored from previous run and we used in previous run, it worked better. But one problem with compile stashing was that it was actually rather expensive to generate the key. So we need to run the front end to generate the IR. We actually need to do this for all inlining candidates, which are part of all the queries.
Yes.
And so
yeah, a big
matching,
chunk of C2 is the parsing. I claim it was stupid, but I mean it could have gotten better, but in the end it was a big chunk. Yeah.
I think our matching in the cache was in the same kind of order of magnitude as C2 compile time for the corresponding methods. Like roughly. But then there was another problem with this, and I think this problem is relevant to any kind of compiled cache. So in order to match, you need to match everything. Like let's say you have some inline tree. You need to match every inline candidate that you have, everything you included. And the larger, the more candidates you inline, the higher the chance of a mismatch.
Right.
So you have very good chance to match small compilations, but significantly lower chance to match large compilations.
And the larger ones are actually probably where you're
they are non-linearly more expensive.
Yeah, more expensive and more likely to get big wins too.
But in a way, they become more unique.
And they become more unique. At the fringes where it doesn't matter, all the little one-offs. You know, a little bit plus or minus on the counter here or there means I inlined this or not. It was kind of middle in. I couldn't. It wouldn't make any difference. No, you were fixed at the. Yeah, okay, I get it. The take the profiles and re-go from the profile looks like
probably also one of those frustrating cases when in development it looks good on micro benchmarks and then you deploy it in production and then you have those larger applications and then you have moments of frustration.
And we discovered a lot of reasons why like code can be slightly different just because of timings, just because of, I don't know, hash code values that were allocated from run to run, all these kind of things.
Yeah, I once was trying to figure out why things varied so quick in a JVM and discovered that within the first 100,000 bytecodes, before you hit main, a million bytecodes get to main, before you hit main, in the first 100,000 bytecodes, people's hash code functions would vary, and then the reprobe loop in the hash table would vary, and the trip count on it would vary, and so you would trigger his compilation earlier or later because the hash code varied, because the hash code depended on what the OS handed you for the start of the virtual memory address from the GC, like something out of the OS.
I think we've seen this very thing, with this caching mechanism.
Stupid things, and suddenly you're different.
And along with the inline or the profile data, do you store if the code is polymorphic, at which types has been specialized? Is does count for what is polymorphic cache or something? I'm not quite.
That's a part of profile, like type histograms for indirect calls, for type checks that's stored in the profile.
Yeah.
Okay, cool.
That's a big one because they're frequently extremely one-sided or bimodal or whatever. They frequently have many options in theory and in practice, extremely small count, and you want to optimize that.
I imagine that code programming language like Python, which is dynamic, this is the most valuable thing, which types the code was called.
I know in JavaScript make a lot of mileage out of that.
Yeah.
All your integers are, in fact, nearly always, but not always, nearly always small. So you badly want to optimize for the small integer case.
Cool.
And then to conclude on the caching story, so we currently have what we call cloud native compiler is when not only the Ready Now profile is served by a server, but also there is a service that you can send compilation requests to and get compiled code from. In there, we have another implementation of compilations cache. It is done differently. It doesn't require building an IR. It uses bytecode and other inputs that the compilation server uses to compile things. So it solves many of the problems that we had in the initial cache mechanism, but I'm not very familiar with the details.
Okay.
About doing any caching in general. Okay, for the profiling, there is actually no. I should probably start. Actually, I'll start with the question before I start with the obvious objection. The question is, with any kind of caching scheme, isn't there sort of a crossover point where actually just doing the compilation from what you already have in memory is faster than loading the results from memory? I mean, not memory, disk or over the network.
Yes. And it varies
Yeah.
about how fast you
Yeah.
can generate code versus how fast,
Yes.
Yes, a C1 compile will happily live out of L1 and L2 and be way, way faster than your disk or your network request.
Yeah.
Yeah.
Because on the disk front, the obvious objection is maybe 10 years ago that'd been a good argument. Nowadays, it's SSDs are fast and kind of cheap. The other thing is, of course, as mentioned, for the profiles avoid warm-ups and deopt cases that do take time independent of actually compiling the codes but still, the one thing I'm thinking about my thesis honors work is that I could use this. I could use what I'm doing to kind of ensure that we have at least some memory safety properties on the cached code. Like if we're loading it from disk, someone can't tamper with the cache and make us get hacked in some nasty way. Same thing over a network. If I was really going to swear by my validation,
well, that's your Java bytecode verifier, right?
Yeah.
Same.
Yeah.
You just have a code verifier or whatever, type assembly verifier. Yep.
Yeah. But yeah, if I'm going to swear by that and hope that I definitely haven't messed anything up, then I could also have never mind having to compile this JavaScript on my phone. Why don't I just get sent a big blob of ARM assembly? Why not? But again, there's kind of depends on the network bandwidth, depends on how beefy the phone is.
That's been around forever and a day.
Has it?
No, you just change the numbers. Here I am sitting up at the mountains. What's my network bandwidth on my phone? Well, it's on the Wi-Fi to the router's pretty quick. If I go to the cell tower, boy, it sucks. The rains come through and go howling and blow 80-mile-an-hour winds, rain uphill between me and the cell tower. It drops to like nothing.
Yeah.
So, those situations of the network is fast, the network is slow, the network has or doesn't have or caches this and that. All those latency things just go in the damn equation that says, how fast is it this way? How fast is that way? I get this much speed up for this way. I get that much for that way after that much latency. You draw the curve. There's a crossover point. You win or you don't accordingly.
Also, for us with the what we call CNC, this compilation service, you may not be significantly faster to make one compilation because of network latencies, etc. But you can have massive parallelism on the server, and in your container, if you are only allocated 2 cores, you will be compiling really slowly and really sad. But you can send compilation requests to the server and have massive parallelism there. So that's how you can win.
I was thinking you get power savings of various kinds. If you have a 10,000 node cluster running the Bird app and you wanted to change some code and you compile it once and then 10,000 servers go suck code over the wire as opposed to do 10,000 compiles of LLVM.
Oh, and this as well. Yeah. Caching and sharing across multiple instances also gives you some savings.
Did you put that link, Aaron, in the doc here? It's a chat link for the doc.
Yeah.
Thank you. I mean, look at the fallacies of distributed. Which one is this fallacy? The network is reliable and latency is 0. Absolutely. No. Sun's big thing was the network was the computer, but that was the most unreliable network I'd ever used in my life at that time. I'd come from Rice University to obviously Motorola, networks run by some contractor guy, to Sun, and Sun had the least reliable network. Fine.
Well, you see where they got it from. it came from Sun, so checks
Yes.
out.
Yes, you could
They
argue
used to talk
that.
about that at Bell Labs, that they had actually made really great network protocols because they had no money, so they had a terrible network. And that if they had had a slightly more reliable network, they would have made much worse protocols.
Gotcha. Okay. All
That
right.
the people who are using the telephone network and
Yeah.
had 10 to the minus 6 error rate came up with these protocols that were just not very resilient. But the Bell Labs group that was doing everything over shoestrings and cups that had
Gotcha.
an error rate of half.
Yeah, okay. Makes a difference. Same for anything, I guess, where you're the tool builder or the tool user.
Yeah,
If
I
you're
wonder
the
if there's
builder
anyone
and the
out there still
user,
using the ATM network instead of TCP.
okay.
But that was one of the things that shocked me when I first started seeing these like transatlantic fiber lines. And the protocols that they use on them basically have no error correction in them because the packet error rate is 10 to the minus 15.
Oh, really? Wow.
And it's just like, oh, this is very different than the environment I was used to in like Wi-Fi.
Oh, yeah. Yeah. Fine. All right. What else? We have any other topics here? But this has been a good conversation. And I didn't know
So
all this stuff. I learned a bunch of stuff about your setup today, Arthur. That was fun.
the question I was going to ask is, as our computers have gotten a lot better and things like the TLB have become gigantic,
Hmm.
has the math changed on whether it's worth it to have a moving runtime versus just like leaving stuff where it was allocated?
You mean a moving collector,
Yeah.
as opposed to
A,
moving
a
code? I
lot
think
of the complexity in C2 is the fact that pointers move.
no, that's not a lot of the complexity in C2.
You don't think the fact that it's
Even
a
if
moving
it was, I
collector
think
makes
it'd be
it
worth it
meaningfully more
still.
complicated?
Wait a second. Okay, Aaron, go ahead and comment, but then I'll hear Yasser. But Aaron first.
I am curious whether people think that the complexity is worth it for the savings
Okay.
of a moving collector that can compact things, even though our
All
TLBs
right.
and chips have become much smarter about having fragmented memory.
I don't personally have a good up-to-date answer. I have my stale answer. So Yasser, what were you going to say?
Yeah, I was going to say that even if it did come at some cost to do pointer moving, I'd argue it's still worth it. So the huge one is that the TLB still has some granularity, like, oh hey, we can only do 4K or like 2 megabytes or something. So if you have if you can't what's it called? If you can't move
Compaction.
any pointers,
Yeah.
then that means that let's say things end up in your old generation and they end up fragmented. That's still potentially like fragmented across multiple 2 megabyte regions that could have been let's say 16 kilobytes if it would have just been compacted.
Right. So
And
you
so
just
like,
said is
Yeah.
TL compaction for the TLB, not for the caches, but for the TLB.
well, the idea would be that if you could tank the hit of what's it called, fragmentation by taking advantage of the TLB, so you could
Yeah.
have a bunch of like pages that
Yeah.
are all just like sparse effectively. But
Yeah.
I'd argue that even so, because the TLB doesn't like operate at like the byte level, that level of fragmentation is still going to hit you in other places like
Yeah.
cache.
Right.
Yeah.
The
That's
TLB is also
Yeah,
not, there's not so many entries.
exactly.
So
Yeah,
once
so
you
even
run
if
out
you
of the
did have
entry,
like a magical byte level TLB, that would actually bring its own problems, like needing
right.
a gigantic cache.
But if you just say the TLB has 64 entries, as soon as I have 65 pieces of hot data that are more than TLB entries apart, I'm
Yeah.
endlessly TLB faulting.
Mhm. Yeah, and then
And
you're
now
paying a
compaction
ton of
makes
dependent
sense.
costs
Yeah,
because
okay.
it's all a
So
bunch of like dependent loads.
so for Aaron, I have no numbers for you, but I suspect same with Yasser, I suspect you still want to move.
Yeah. Also, I feel like managing a segmented heap will have its own complexity,
Yeah. Yeah.
and yeah, I don't know.
So you
It's
think a
hard to compare.
non-moving system may not even be a complexity win, nonetheless a performance win?
Um, Hard to tell. There will be some
Hmm.
complexity. Like there is something nice about being able to like just move everything and just have a single chunk. Although I don't know, modern collectors might be
There are
already
other
dealing
things
with
that
this
can
kind
be
of stuff.
done with the moving collector that we as an industry have not yet done that would be exciting, I think, if somebody would do it. And that would
Such as?
the Azul collector could restructure how an object looks because it can dynamically change what every pointer does on the fly incrementally.
In
And that
Did you
means
say
I
which
can,
structure? You mean like struct of arrays versus array of structures?
that too. Just much simpler. Profile after a while. How many fields in this Java object are 0 and have been 0 their entire life? And now I want to go recompile where I shrink all the zeros out and I tell the interpreter and the JITs that if you ever want to write a non-zero into these fields, you have to like stop and recorrect. But otherwise, the object shrinks from 50 fields to 7 and becomes hugely smaller. And if you read from such a field, the compiler just inlines the 0 for you. And if you write to the field that's non-zero, then he halts and deops and tries again. And now I can shrink all your 0 fields. And by God, I know in these big Java apps, there are a bajillion fields that are always
So
0 all the time.
it will compact the object representation
It
significantly.
compacts the object representation on the fly. Yeah. And I can make that happen in a wave in the Azul collector where he rotates everybody on first touch, but you have to make the wave tie with the wave in the JITted code, but you could do that too. And then, in case of Arthur's case, you could record that info and start it up next time around. He could make the initial assumption. Don't make any of these fat objects. All these fields we're gonna init them to 0 and pretend they're 0. And if we're wrong, we'll have to do the hard thing. But profile's good. We're not wrong. Well, all the objects shrink by a lot.
Well, I know of one case. I know of one when in the GC, for moving and non-moving, one bit you do get a bit more complexity with non-moving generational GC. If you so want to compact everything at all times, what you can do with your heap is that you can arrange it such that there's some line in some pointer, some address line in the sand where everything to the left of it's old, everything to the right of it's new. If not that, say Steel Bank is mostly copying conservative roots, blah 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 blah. Then at that point, you can assign every page a generation, and so you have still fairly coarse-grained metadata, not a whole lot of it. In my collector, which is mostly non-moving, it tries everything it can to not move. The metadata has to be even more finer grained, up to the 128 byte, and that makes a lot of metadata, and it kind of ends up with this kind of two-level hierarchy of metadata, which is also just all around more code and more slow, and so
it sounds like
and
a lot
also
of
yeah
performance lost right there.
yeah.
It's grain to tracking.
Yeah, and there's also another bit. With fully non-moving, as in Boehm, GC, BDW, such, there's also more that also plays interesting with card marks, because now you can have both old new objects on the same card, and now writes to new make you look at your old cards. I narrowly avoided that because I define the card size to be the line size for IMIX, and therefore, just by how the allocator works, we're not going to have multiple generations on the one card. But we still have a heck of a lot of cards. In a 1 gig heap, you have one every 128 bytes still. That gives you 8 million cards that you need to look at. No, thank you. Which is why now I have to look at doing a logging barrier, so I don't have to look the whole thing. And sometimes that's hilariously faster, sometimes that's not too much slower. So I think that might work out.
Right. But
does it make sense to have trees if you have too many cards? That's like, this is the node that tells you about this collection of cards so that I can skipping on.
Yeah, there are papers on doing that. You have like a 2-level card table. However, what I'm scared of about doing a card level table is, first off, that's just more code for the write barrier. Yes. And write barrier goes slow, everyone's sad. Second off, if I have cores, I've also had nasty incidents about false sharing in the card table. Yes. This alluded, I'm not joking when I say that I only recently found out that I was only getting bitten by false sharing in the card table after about 2 years of not wondering why one benchmark was weird when I built steel banks with one particular set of flags and not another one, because I didn't know what the magic thing you're supposed to put into perf to tell me about false sharing was. Now I found out, and now I'm deeply embarrassed. But if I was to do a 2-level card scheme, I'm also worried that I'll just end up with more false sharing on the coarse-grained one because everything is going to map to the same cards.
Certainly, the Azul collector went back and forth on whether or not we wanted to do guarded on card marks to avoid false sharing. Exactly.
Oh yes, yes, yes. Going from no guard and card marks was, that was false sharing. I start adding cards. Hey, why is this parallel program 40% faster? I don't know. I haven't done anything to the GC yet. And now when you add, and indeed when you add the log to it, now hopefully I can make the GC faster because it's not looking at 8 million cards per gigabyte, hopefully.
Yeah.
That might be, yeah. So that's all.
And then
So that's, yeah. So my thesis there is that you can definitely make some pretty copying collectors that have less complexity. Although on the other hand, it's a weird trade-off, but it's a weird trade-off because you don't want to be non-moving all the time for locality, but you also don't want to be moving all the time. So you have to strike a balance, and
So
I think maybe I went a bit too close to non-moving, to be honest.
C4 does it by looking at sparse pages.
Yeah.
So TLB pages that go sparse. And then he compacts just the sparse pages.
Yeah. Because I think I want to say same thing in G1.
Oh, maybe. Yeah.
Yeah, because that's evacuating just the sparse pages.
Yeah.
Even though it traces all the pages, Imix is kind of that, except it's also just able to reuse lines, 128 byte runs in place as well. And yeah, so that's what I did. And in fact, I just did that 128 byte runs thing, non-moving at first, and I added the compaction later. But yeah, so all that to say is that TLB, I'm not sure. To be honest, everything else, I think having some degree of moving just leaves you with less metadata and leaves you with simpler code, I think.
Are you talking concurrent yet?
Concurrent, maybe someday. Someday, yeah, because I did the non-moving first because I think maybe because well, Cliff might disagree with me on this one, but I'm going to say actually no, Cliff might agree with me on this one. Steelbank is not architected for concurrent moving.
Oh.
No read barriers.
I could agree with that one.
Okay, so I don't want to go down that hellhole for a while.
I have no idea.
So I'm just going to go for concurrent don't move and compaction we only do once every while. And again, we're only compacting a little bit at a time, so maybe I can get away with doing it in a pause because I don't think anyone's using this for high frequency trading just yet. Hopefully.
Well, if they were, you'd be getting a reasonable salary.
Yeah, I was just about to say. If there is anyone using Steelbank Common List for high frequency trading,
go ahead.
There could be people on this call who get paid by high frequency traders and I have no idea, might be hiring people who are experts on concurrent GCs.
If anyone here is using Steelbank Common List for high frequency trading and they want their collector.
I didn't say common list.
Oh, I can't even have the easy way out on
finding
this.
Somebody who's an expert on implementing concurrent GCs is a tough call already.
Well, I haven't done GC. I haven't done concurrent yet, so maybe I shouldn't overstep here.
So would it be beneficial if you have some runs that are not compacting? So if you enter a region that, let's say, it's a high frequency trading or something, and you generate garbage for the sake of the speed, and then on the next run you compact it.
Yeah. There's definitely we only want to trigger compaction when there's like significant fragmentation. Is or the other fun thing, which I don't entirely know how to measure, is if we lose locality as well. But it's really we only want to want to compact it. It's a trade-off,
of course, because you want the speed for now, but you leave more stuff for later. So
you might be able to pick up the locality by watching your L2 cache.
Yeah. And of course, there is another fun thing. If you had a read barrier, then just by when you trip the read barrier, you're going to start copying all the connected objects together, which kind of implicitly gives you some degree of, kind of picking the right order.
relocate stuff.
I have read some article years ago that when C2 notice that it's a linked list, it will try to hold objects next to each other, so to preserve locality.
No, C2 doesn't try. It is the nature of the program itself that if you make a linked list, it is commonly the case that you make it all at once, maybe with other things. So you put a linked list header and then you made some crappy stuff and you made a linked list header and more and more and more, and they alternate. After you compact, the walker walked the linked list in order. So nothing to do with C2.
Okay.
And compacts all the link headers together because the stuff in the middle just died.
It's a side effect of compaction.
As a side effect of compaction, if you allocated temporary things to make your list entries and you're running single threaded, then each thread says list entry, temp stuff, list entry, temp stuff, list entry, temp stuff. Temps go away, you compact by following the next. Got it.
An interesting transformation would be if you detect that instead of linked list, it will make a hybrid list, a linked list of array list
That's a
or
data
something.
structure change, and then that's like not what the compiler's doing. You'd
That was
love
something
to
I tried to play around with
Ponylang
trying to
does
compile.
because
wait, okay, Yasser's
sorry,
turn to go first.
So that was something I tried to play around with in terms of converting linked lists to arrays, because I was trying to do that for I wanted to do like a Lisp runtime, except I wanted to play around with the whole idea of restructuring data like at runtime, but it is such a nightmare because you just run into like needing a bunch of barriers that describe like, oh, you can do this as long as these assumptions are held, and like they're usually held until they're not, and in which case everything explodes, and I have to like figure out, I have to make sure to write all the cases. So like I will eventually get around to it because it is fun, but I have to write all of the like slow paths first, and then I can worry about the fast paths, because at some point everything is going to fall back to, oh yeah, I need to link this at some point, like a real linked list.
Yeah.
I wanted to do the same thing with like.
Wait. Yeah. I cut off Aaron because you two tied. So Aaron, go.
Right. My question was whether anyone had looked at Pony, because I know they're both used a lot by high-speed traders and have a GC. And I don't
they
really
are used
know
by high-speed traders?
What they do.
I definitely looked at Pony some years ago.
I've never seen it used by high-speed traders.
Yeah, I hadn't heard that one. They have the concurrency thing where they can, rescue themselves, so sort of elegant concurrency or elegant sharing across threads. But I mean, beyond a bare industry, academic implementation, I hadn't heard anything more. So you heard something about high-frequency traders there?
I had heard that Bear Stearns was using it, but I could be wrong.
I don't know.
I don't have a citation to give you, so.
Yeah, right. No. I ran around that.
Bear Stearns hasn't been around for a while.
Decade. Didn't they get picked up by somebody? They
died like 20 years ago.
I thought somebody picked them up a long time ago.
And Pony's younger than that?
Oh, no, Pony's not that young.
Yeah.
But
maybe it killed them. I don't know.
Time to go find some references to Pony. Pony might be still kicking around. It was somebody's pet project here. Pony language, see if I get a hit here.
But mostly what I know about it is people talking about the weirdness of their type system and whether a pointer is shared or not shared.
It's not
type system.
Bear Stearns died 16 years ago.
And I claim that Pony's type system isn't super weird around that piece. Other parts of it maybe were weirder. There's an active web page. They claim there's a GitHub, which probably will have a last time something got fixed was 2 weeks ago. Ponylang.github.io has an update as of 2 weeks ago and 1,000 commits it's reporting. So I claim it's not dead. That's interesting. And then Ponylang.io, I should put Ponylang. Let me put Ponylang.io in the doc. They hadn't hit it already. Yeah. Right. So it's out there. Now, is it interesting? Try it in your browser. Tutorial. Okay. No official roadmap. Pony prevents data races. It can't stop you from writing race conditions in your program. Here's a couple examples of some interestingly complicated programs written in Pony. There's no formatter for the pony code. That must have come around from the Go. One other thing here. 30 seconds in the tutorial. Type safe all the way. Oh, I see. And then, all right, never mind. I have to go stare at it. I claim it had some other things going on with it that were not related to the interesting parts they were doing with concurrency that may or may not make it exciting language. Out there still.
I do still think it's an interesting idea to have unique pointer as a different type from all of the pointers are in the same sequential process, so you can assume no one else is touching it.
Yeah.
Interleaved with you versus there exists at least the possibility of some pointer outside of your sequential process.
No, I'm 100% on board.
Like this middle level of it's not a unique pointer, but neither is it a pointer shared with a different sequential process is interesting.
I like what Pony did there. I remember thinking there were some other things they were doing, and I hated their syntax. Maybe something to stare at. I had, grand plans for AA where I would stare at the Pony parallel stuff again and see what makes sense.
The other one I wonder is, does it need to bleed into your language, or can that be a concept that you do entirely in the runtime?
Oh, Pony is like Rust mutability that bled into the type annotation.
Right. So in Rust, all the complexity bleeds into the language. I have to think about, is this a shared pointer or is this a unique pointer?
Yeah, I'm claiming it did. I mean, does it have to? I don't know. It did bleed in. Like, if it doesn't have to, like, can I do inferencing here? I don't know how else you're not going to.
Java knows things about my types that my code does not. Or the JVM knows things that
you mean erase the generics?
Bitcode doesn't. Yeah.
Yeah, that's the stupid thing for how generics went with the VM as opposed to keeping them around. It certainly didn't have to be.
Right. So you can imagine a runtime that the runtime is making smart decisions because it knows there's no other thread that could possibly be sharing the thing. So it can use an implementation that's not a thread safe implementation.
Oh, a JVM can know for like particular type that you don't have any implementer, any like subtypes there. So it would optimize CHA accordingly. So in a way it does. Yeah.
So in Azul, I did stack-based allocation for quite a while. I worked on it pretty hard. And one of the things that came out of that was I would have a collection of pointers that I knew were thread local. And I knew them at the time that I could JIT for them, so I could take shortcuts on like locking and shit. It's a little weird because when you call the function, he had to know that he was only going to be called in a stack local context. But then he could take shortcuts on locks.
So did you have to go flavor all of the functions to be like, can the arguments escape?
I didn't make it official. So there was some hacking I did where I said, I know that this guy gets he could tell at compile time, you go ask the question. Tell compile time he's running in a thread local context, but he didn't have an official bailout path on the JITted code installed. So for all my like easy short test cases where no one was cheating, the first run you got the level of stack depth necessary and you were not in heap. That got pretty stable fairly quickly for some interesting large JBoss, interesting large apps. And then I went in and JITted code that were cheating. And had JBoss then broken the rules, I wouldn't have caught it and been dead. It was worth something on top of the stack local GC, which was also worth something.
By the way, speaking of the lifetimes and Pony, there is this interesting work by Andras Kovac, lightweight region memory management in a two-stage language, when he kind of starts from the opposite side than Rust does, is that he starts with a garbage collected language as the baseline, and then he adds regions in the type system to relieve the pressure of the garbage collector. So you kind of end up with an ergonomic language when you don't really have to do that much annotations for the lifetimes like you have to do in Rust. But you still don't have that much garbage collection pressure by default. So I think that's an interesting direction. I posted some links in there.
Rust viewpoint is by object, but languages like Vale 2 considers regions that are read only or something that can more efficiently track the ownership.
One of the reasons that I like the whole arena like thing is that you get performance out. If you can recycle the same memory
Yeah.
and it fits in a cache, that's way faster than, GC never fits in a cache.
So most of the apps nowadays are request based, so you can write up nearly half of the memory that you generated and reuse it on each request.
You talking about with arenas?
Yes.
Yeah, I was just saying, where do you? Oh, if you have a C app or something, you get an arena out of it all the time. People hand roll those.
Yes.
I'm talking about garbage collected language with arena-like discovery.
Yeah, discover that your app is a request response based, and you can reuse the memory from the previous request.
So
I can't go.
So that's the example I always reach for is you have a web server that's basically got 3 piles of memory.
Yeah.
There's the stuff that got allocated as you were initting that are essentially globals.
Right.
There's the stuff that's in the cache that a bunch of web requests are trying to share. And then there's the context of your web request where at the end of each, you go 15 milliseconds, 150 milliseconds, and then you blow away that arena and you keep rebuilding that request and blowing it away.
The concurrency and asynchronously features will make that more complicated. But
somehow the runtime has to figure out when I allocate a thing that it's destined for the cache, not that it's going to blow up with my arena. So I have to do something that detects the escape.
Picked up on
you guys.
Case. Sorry,
you guys make me want to finish my language, but too many lines of code to write. Every month, something you guys say makes me want to finish it.
Stack allocation, discovery, escape detection, not escape analysis, was working at Azul and would exactly pick up these patterns. That's why I said it worked pretty well on JBoss, which was doing request response behaviors. Individual threads.
Yeah, I'm fine with escape detection because some amount of copying is going to happen somewhere.
Yeah, some of it escaped, but I didn't have to do an analysis that would just fail. I would just optimistically assume and then run the check, and then you had a runtime, or you had a read barrier or write barrier, you had a write barrier, had a little more cost to it, and you typically didn't fail the barrier. And then I was getting 70% of all allocations stack allocated on these busy threads.
I'm thinking of as Matt mentioned, doing the opposite direction from Rust and such. I'm thinking of doing something of the sort, doing escape detection, regions, thread local, GC. All seems very interesting. Again, coming from, oh dear, I wrote a parallel GC. If only I could just spin up n many copies of my GC instead of having to parallelize this one big GC. That'd be very nice.
You need to get your advisor to agree to sign off on that. Or pick an advisor that will sign off on that.
Oh, I already know someone. Who's doing redoing the thread local GC. Actually, I can think of a couple. Well, one here. There's also the parallel ML Mabel. They have a pretty neat thing because they're just doing fork join parallelisms. They can do some very clever things about who's able to see what and what can go up and down the fork join tree. Oh dear, and I was thinking that also about object unrolling, flattening, list unfolding. That this is all awfully convenient with immutable objects, because first off, if you don't write, there's no write barriers. Definitionally, and also when you get an escape, you don't have to fix any pointers. But you can just copy. The extreme of this is something like Erlang, where you only have process local heaps, and every message send is doing a copy, essentially. I think maybe you do want a global heap, but the immutable thing, you can just get lazy and copy everything.
Erlang's
model, n plus 1 GCs is better than n GCs, one for each thread, and one more for the global.
And then one more for the global. That's what I ended up at. One per thread and one for And the one per thread was run by the self thread, which was all hot in his cache.
That seems interesting. But there's already someone redoing the thread local for Java. Because there's already
some things to look out for.
There's all
giant objects that are still thread local, and then you badly want to have generational because they're giant, not moving, but they're thread local, and you don't want to revisit them. And then the similar one was a very busy thread, and just one producing tons of thread local garbage, still wanted a parallel collector. to clean it up because he was doing so much garbage production.
Yeah, I do have far too many. I have far too many references on this because in somewhere I just mentioned we have immutable objects. Here's a very long list of fun things you can do with immutable objects in the implementation.
Yeah.
Go nuts. Yeah, here. Yeah.
All
You know what they
I
say,
have-
immutability changes everything.
Yes. There we are.
I hadn't heard that one, but that's good. All right.
Yeah, because we got, let's see, implementation may pass, you can unbox across the calling convention. Of course, instead of pointer to a tuple, you pass all the tuple arguments, of course. Deduplicate, you can hash cons in the GC if you so feel like it.
Yes.
Inline, unroll objects into each other.
Now, does pointer equality change when you hash cons?
Yeah.
Of course it does.
If you do immutable objects, you promise very nicely to not start looking at pointer identity. So bad programmer, either you don't have it in the language, or you just say this can fail, this can lie at any time. Don't use it. So inline, deduplicate hash cons, unroll objects into each other, and otherwise play loosely with identity in order to provide more efficient memory management. Oh yes, also no read barriers either, I think, because you don't have to, you can just leave. The mutators can just look at either version of the object if all the objects are going to be isomorphic.
All right, I am going to put an end to this here.
Okay.
Anyone want to have any last words before we declare victory and walk away?
No?
All right.
Fun stuff.
Levo, one language, please.
But make the memory management thing work. Damn it. All right, fine. Till we meet again. Bye-bye.
Bye-bye.